What's up, everybody? Here are the solutions for the last part of the final review, which is applications of integration. And we'll start with problem 33, part A, which has us look at finding the area between two curves, right? The first curve is y equals x to the fourth minus 5x squared plus 4, and the second curve is y equals negative x squared plus 1. So the first thing we need to do is figure out what the region looks like, and what we have here is you can either do it on a graphing calculator, or you can simply factor this, and you'll see that when you set the two curves equal to each other, you move everything to one side, you end up with the polynomial x to the fourth minus 4x squared plus 3, which factors as x squared. I need numbers that multiply to 3 and add up to 4, so x squared minus 1 and x squared minus 3. So the intersection points are at x equals plus and minus 1 and plus and minus square root of 3 from the second parenthesis. Now let me give a rough sketch of this region. First, I have the x to the fourth polynomial, and it looks something like this. And then I have the negative x squared plus 1, so it's the parabola that's shifted up 1, opening down like that. Right, so the region of intersection is the shaded region right here. That's just a rough sketch. And the area is going to be comprised of three integrals, right? Because when we find area, we take the top curve minus the bottom curve. And as I move from one region to the next, the area of the first region, area 1, the top curve is going to be the parabola part. As I move to region 2, the top curve is going to be the x to the fourth polynomial. And as I move to region 3, the top curve is going to be, again, the parabola part. So to find the total area, that's going to be the sum of the three. And notice region A1 and A3 are symmetrical, so actually when I just do the area of A1, I can simply multiply that by 2, and that gives me the area of A3. So I get, well, what's the area of A1? It should be the integral from negative root 3 to minus 1. Top curve is the x to the x squared part minus the bottom curve, which is x to the fourth minus 5x squared plus 4 dx, and that gives me the area of region 3. Now I'm going to multiply that by 2, and that also gives me the area of region 1 and area of region 3. But then I have to add the area of region 2, which is the integral between minus 1 and 1 of, now the top curve is going to be the x to the fourth polynomial plus 4 minus the parabola. And that right here is the formula for the total area. Right? It's a sum of three different pieces. Let's move on to, I won't do part B because I was talking to Professor Ruppel and there is a typo there, so I'll move straight up to part C. I'm looking at the area between y equals cosine of pi x and y equals 4x squared minus 1. So let's quickly draw that region. Cosine of pi x is going to look just like cosine of x but instead of having zeros at pi over 2 and so on, it'll simply have zeros at the integers. So this is what the graph is going to look like. I'm still up at 1. That's the cosine part. Right, and then it will just continue. So the 0 here is at x equals a half and x equals negative a half. And the parabola 4x squared minus 1, notice it is shifted down 1, and when I plug in a half into it, I get exactly 0, so it should look like this. So the region of intersection is the shaded area over here. So that means the area is simply the integral from minus a half to a half of top curve, which is cosine, minus the bottom curve, which is 4x squared minus 1 dx. So that integral gives you the area of that region. Let's finally move on to part 33D. And for this one, we're looking at the curves y equals secant squared of x and y equals 8 cosine of x. So let's quickly sketch what that looks like. I know that for the secant graph, I am going to have vertical asymptote, even if I square it, at minus pi over 2 and plus pi over 2. And it's going to look something like this. Be
just like the cosine graph, except it's shifted like that, and it's going to hit 0 precisely on the axes, just like so, and then it will just continue to do this. So the region we're interested in is over here, and the thing that I need to do next is find these two intersection points. So I'm going to set the two curves equal to each other, but instead of writing it as secant, I'm going to write it as 1 over cosine. So I have 1 over cosine squared equals to 8 cosine x, which means cosine cubed of x is 1 over 8, and once I apply the cubic root, I simply get cosine x equals a half, and that tells me that x is equal to plus and minus pi over 3, and I get that simply by considering the 30, 60, 90 triangle 1, 2, root 3. The angle for which the cosine is a half is the highlighted angle, and that's pi over 3, or 60 degrees. So now I'm able to set up the integral. The integral for the area is going to be integral from minus pi over 3 to plus pi over 3. The top curve is the 8th cosine. The bottom curve is the secant squared dx. And then you just integrate this. So that's problem 33. Now let's move on to problem 34, which is really the meat of this section, which has us compute volumes of solids of revolution and other solids as well, solids of known cross-section. So problem 34, we'll start with part A, has us look at the solid of the whose base of the region is bounded by the following curves: y equals x cubed and y equals, not y equals, but x equals y squared, and whose cross-section is perpendicular to the axes, and it's a square. So let's go ahead and quickly sketch at least the base of this region. And the y equals x cubed, we all know it looks something like that, and then it would continue on the negative side like this.
whereas y equals negative x squared, x equals y squared would simply look like this. It would be a parabola, but it would be on the x-axis. So here is the region that is going to form the base for our solid. Now I made a quick sketch earlier when I was doing the solution of this problem. So this is what the solid would look like, with cross sections being squares, and the cross sections that I'm highlighting here are exactly these three lines that I drew in the region on the 2D plane. So that's the solid that we're looking at, and to compute its volume, because the cross sections are square, I simply integrate the area of the cross section, which is side length squared dx, and the integral is going to go, well, this intersection point is 1, 1, so I go from x equals negative 1 to x equals 1, and the side length is simply top curve minus bottom curve here. So the side length is going to be given by, top curve is square root of x, because if I have to solve for y here, right, so y equals the positive square root of x, and let me see, is that correct? Yes, exactly right. This is, if I highlight this shape, this is just the graph of square root of x, and the bottom curve is going to be x cubed. But I square the side length, so that's the integral for the volume of this shape. Now let's move on to part B. So part B now has us look at the same region, but the cross sections now are perpendicular to the y-axis, and they are semicircles. Okay, so that means the area of a cross section, in terms of this time is going to be in terms of y, since they are perpendicular to the y-axis, and that's going to be given by, okay, if I have something that's perpendicular to the y-axis, now I have to compute this, and the diameter would be a semicircle like that. So the top curve now is cubic root of x, cubic root of y. I just solve for x in this equation here, so I get x equals cubic root of y minus the bottom curve is y squared. So that gives me the diameter. Now I need to obtain the radius, so I divided the diameter by 2, and I have to square it. So really what I'm doing is dividing by 4. So this is r squared, and I multiply by pi, because the area of a circle is pi r squared. However, because when I square it, that's just
the radius, this gives me the area of the whole circle, so I just multiply by half to get the semicircle. Okay, so over here, the first part where I'm dividing by 2 is because I'm looking at the numerator here being the diameter squared, right? So I want just the radius, multiply by pi to get area, and a half to get the fact that these are just semicircles, not whole circles. So now the volume of this is, of course, the integral of a dy. So let's see, the integral is going to go, well, I know the bounds, it goes from y equals 0 to y equals 1. Oh, and I just realized I made a mistake earlier. Here we should start at x equals 0, so I apologize for that. So we go from y equals 0 to y equals 1, and what are we integrating? It's 1/2 the area of the circle, so it's 1/2 pi
and this is the radius. Squared dy. So that's this piece right here. Okay, so that's 34b. That wasn't too complicated, but now we're looking at a slightly more interesting area. So let's go to 34c, and let me find where the question is on my sheets of paper. So for 34c now, the base of the region is going to be a triangle with the following vertex structure. I have a vertex at -1, 1, at 0, 0, and at 2, 1. So the region looks like a very thin triangle, just like so. Okay, so this is the point -1, 1. This is the point 0, 0, and this is the point 1, 2, not 2, 1. It's early in the morning. And we have to figure out what the region is bounded by in order to be able to compute distances. So this is the curve y equals 2x. This side right here is given by the curve y equals x. And the larger side is given by the curve y equals 1/2 plus 3/2 x. Okay, and the cross sections are going to be perpendicular to the x-axis. So a typical cross section would have the following base. Now I'm told that the base B is it's an isosceles right triangle. So this right here is the base of the triangle, and I'm highlighting it here as I highlighted it in my drawing here for the cross section. Let's label that side B, and I need to compute the area of the cross section before I can do anything, right? So using the Pythagorean theorem, what do I have? I have that a squared plus a squared equals b squared. So a squared is b squared divided by 2, and the area is base times height, right? So these are perpendicular. I can take one of them to be the height, divided by 2. So that means the area of the cross section is gonna be b squared divided by 4, because I just divide the whole equation here by 2, and that's the area of the triangle. Now the volume, yes, the volume now is going to be the following. Notice that between x equals -1 and x equals 0, I am bounded above by this curve and bounded above by the same curve.
But below is by y equals 2x, so that means I have to split this into two integrals. First integral is going to go from -1 to 0, and what I'm integrating is 1/4 b squared, so 1/4 the area of the base is top curve, which is 1/2 plus 3/2 x, minus the bottom curve, so minus y equals x, and I'm squaring it. So that's the b squared part in this formula here, dx, plus I also have to do the integral now from 0 to 1, 1/4. The top curve is the same one, 1/2 plus 3/2 x, minus, now this time the bottom curve is 2x, and I'm squaring it because I need b squared here. So this volume has to be expressed as a sum of two integrals.
And that was problem 34C. Now let's move on to the tough one, which is 34D. Okay. What I'm looking at here is I'm looking at the region bounded by the curve y equals negative x squared and y equals x to the fourth minus 6x squared plus 4. So let's give a quick sketch of this region, see what it looks like. Here's the fourth degree polynomial, roughly. And here is the x squared polynomial. I'm drawing it kind of large so that I can actually get that's a
Bounded. It's really given by three different regions. I'm going to call this region 1. The middle one is going to be region 2, and the last one is going to be region 3. Okay? And I can quickly figure out the intersection points by setting these two equal to each other. So I get x to the fourth minus 5x squared plus 4 equals 0, which factors as x squared minus 4, x squared minus 1 equals 0. So that means x is equal plus and minus 1 and plus and minus 2. These are my intersection points, or at least their x coordinates. Okay, now for the first part, so I have the region drawn. Let's do it piece by piece, right? So for the first part, Roman numeral 1, I'm looking at revolving this about x equals 3 and using this cylindrical shell method. So here are my regions. And I'm revolving it about a vertical line, x equals 3, right? So if I use the cylindrical shell method, I want to take a very thin cylindrical shell and I want to compute its I want to compute the radius rho, and I also want to compute the height. So the radius rho is simply going to be x equals 3 is the most positive of the two, minus the x coordinate as I'm running over this region. So it's 3 minus x, and the height is going to depend on which region I'm talking about, right? But it's always going to be the top curve minus the bottom curve. And if I'm in region 1, notice the top curve is the x squared equation. The same is true for region 3. But if I'm in region 2, the top curve becomes the x to the fourth polynomial. So let's quickly write down a formula for this integral. It's going to end up being a sum of two integrals. So the volume is the volume over region 1 plus the volume over region 2 plus the volume over given when I rotate region 3. And what do I end up with? Let's see. Over region 1, I have the integral, I have 2 pi times the integral minus 2 to minus 1 of rho h dx, right? So I have 3 minus x, h is top curve, dx, plus, now the volume over region 2 is 2 pi integral from minus 1 is gonna be same row, except this time around the top curve is the 4th degree polynomial. The bottom curve is the x squared. And for the last integral, I have 2 pi integral 1 to 2, same row, but the h now becomes the same as in the first integral. So that gives you the volume for the entire, region 1, region 2, and region 3 revolved. Let's go ahead and move on to part 2. So Roman numeral 2 has us look at revolving the same one about x equals minus 4 using the cylindrical shell method again. Well, what's going to happen is the heights are going to be the same because I'm still revolving about a vertical line. However, this time the radius rho will change. What I'm doing is x minus negative 4, because negative 4 is to the left of everything. So I do the more positive, which would be the x coordinate as I'm doing the integral, minus the more negative. So it should be x plus 4. So now the volume is going to be the volume over region 1, which is 2 pi integral minus 2 to minus 1. The rho, instead of what it was, it becomes x minus 4, x plus 4, times top curve minus bottom curve for the height. Plus 2 pi, the integral for region 2, minus the bottom curve, plus the integral for region 3. So that goes from 1 to 2, x plus 4 times the height. So that's part 2. Now let's move on to part 3. I am using now the washer method, and I'm revolving this about y equals 4 using washers. So for the washer method, in region 1, because I'm using washers, I need the inner radius and the outer radius. So the big radius, the outer radius, is going to be, well, let's see. Let me quickly sketch or go back to what my region was on this other side. So I'm revolving it about a horizontal line. Now, the outer radius is the distance between that line and my curve that I'm revolving about here. So this line is y equals 4. And the inner radius is the distance between the other curve, right? So the outermost here is looking like it's the 4th degree polynomial, and the innermost is the 2nd degree polynomial. But I have to take that as a distance from the line y equals 4. So it is 4 minus the 4th degree polynomial. And the little radius is going to be 4 minus the x squared curve. For region 2, what I have now is going to be
the big radius, this becomes on top, right? So it's going to be 4, and I'm just going to forget about the negative signs. 4 plus x squared. The little radius is going to be negative x to the 4th plus 6x squared. And for region 3, they are again going to be just like in region 1. So now if I want to compute the volume for this, notice that region 1 and region 3 are going to be the same. So I can simply take twice the integral for region 1. So it's going to be 2 times pi big radius squared minus little radius squared. And what I end up here is big radius is negative x to the 4th plus 6x squared, quantity squared, minus 4 plus x squared, quantity squared, dx. So that's the volume for region 1 and region 2 combined, and now I have region 3 combined, and now I have to add the volume for region 2. So it's pi integral from -1 to 1 of big radius is the other function squared minus the little radius squared. So that gives you the volume for part 3. Now let's quickly do part 4. And the difference between part 3 and part 4 is when I compute the radii. So for region 1, before I did constant because y equals 4 was on top of everything, minus function. This time I do function minus the constant. So I have the big radius is going to be, well, let's see. In region 1, it looks like the x squared is going to be on top this time around. So the outer radius is given by x squared minus constant. Or negative x squared minus negative 6, which is 6 minus x squared. And the little radius is x to the 4th minus 6x squared plus 4 minus 6. Similarly for region 2, this time is the 4th degree polynomial that's on top. So the outer radius is going to be given by x to the 4th minus 6x squared plus minus 2, so I'll just do the computation here, combining the constants. And the little radius is going to be equal to 6 minus x squared. And region 3, same as region 1. So the volume here is twice the integral from region 1. And the reason why it's twice is because I also want to account for region 3 all in one. So shoot 2 rabbits with 1 stone. And now I have the outer radius squared minus the inner radius squared. The integral from region
2
So it's the outer radius, I square that, minus the inner radius squared. So that is what I'm looking at. Hang on a second, let me think. I think I may have made a mistake. For it should be minus -6, because I'm revolving about y equals -6. So really this constant, it's not -2, it's plus 10. So let me fix that real quick. Okay, so now that's the correct formula for the integral. Okay, so that takes care of 32 part B, and I'm going to now do 32 part E, which is the more complicated part, but I'll only look at the region in the middle for the intersection of the two curves. So let's take a look at, 34 E. The region of intersection looks something like this, and I'm revolving for the Roman numeral 1 about x equals 3 using washers. So if I'm using washers about a vertical line, what's going to happen is I need an inner radius and an outer radius. And notice that these are going to all depend on y. Okay? And the general rule is whenever I revolve, let's see, if I revolve about the, say, x axis or something that's horizontal, if I use the washer method, then the thickness is going to be given by dx, so I have to do an integral with respect to x. But if I use the cylindrical shell method, the thickness, the integral is going to be with respect to y. So it's going to be with respect to the other thing. I'm sorry, I think I got this one wrong. Let me think. If I revolve
So I'm revolving, let's say I'm revolving this curve. Yeah, if I use the washer method, the thickness is dx, and the cylindrical shell is a integral with respect to y. If I revolve about a y-axis or something vertical, if I use the washer method, it's going to be an integral with respect to y, and if I use the cylindrical shell, it's going to be an integral with respect to x. So in this case, I'm revolving, notice, about a vertical line, and I need to use the washer method. So I have to give an integral with respect to y, which means the first thing
that I need to do here in this problem is I need to solve for all of these curves, right, and write them as functions of y rather than what they're given, which is functions of x. So for the first curve, the fourth degree polynomial, I'm looking at y equals x to the fourth minus 6x squared, and what I'm going to do now is complete this square. So plus 9 minus 5 is that constant of 4, right? But the first piece right here is the completed square, so I can write y as x squared minus 3 quantity squared minus 5. So now I just solve for x as a function of y, because I need to do an integral with respect to y here. So what's going to happen is I move 5 to the other side, so x squared minus 3, once I apply the square root, is the square root of y plus 5, and I move 3 and then I apply another square root, so x is going to be plus or minus square root, and under the big one I have square root of y plus 5 plus 3. Now notice this is 2 branches. This branch here is going to be the positive root, so I have plus square root of square root y plus 5 plus 3. This right here is going to be the negative root. And I have to do the same thing with the parabola, so I'll do it down here. We have y equals negative x squared, so x squared is minus y, and x is plus or minus square root of negative y. So let's label that. The positive root is going to be this branch, and the negative root, so we have
all of the curves as functions of y. I'm ready to use the washer method. Let me split this into three regions. The region 1 is going to be down here. Region 2 is going to be down here. Let me call that region 3 to be consistent. And region 2 is the bigger region in the middle, okay? So now for the volume of region 1, given by when I revolve region 1, notice that what I'll have is I'll have an outer radius that's going to be 3 minus the function, and the outermost function is minus the negative root, so it's going to be 3 plus the square root y plus 5 plus 3, and the little radius is going to be 3 minus the negative root of negative y, right? So that becomes positive, just like so. For the volume of region 2, the bigger radius is going to be 3 minus the negative root and for the little radius is 3 minus the positive root. Because this is strictly bounded by the fourth degree polynomial that we had. And for the volume of region 3, the big radius is going to be 3 minus the positive root of the quadratic, and the little radius is going to be 3 minus the positive root of the fourth degree polynomial. So using this information,
That means the volume over region 1 I obtain by doing the following integral, and this is the Washer method, so remember I have to do pi big radius squared minus little radius squared, and the integral is going to go from y goes from -1 to 0 if I just consider, okay, this is y equals -1 and I go all the way up to y equals 0. The integral goes in the y direction, and I now just have big radius squared so it's 3 plus square root y plus 5 plus 3 quantity squared minus the little radius squared, so 3 plus square root of negative y quantity squared dy. That's the volume of region 1 there. For the second one is pi integral y is going to go from 0 to 4, because 4 is the maximum, is the tip point of this 4th degree polynomial. Right, so y runs from y equals 0 all the way up to y equals 4. And I have big radius squared, so 3 plus the root minus little radius squared, so it's 3 minus the root and of course I still need to do the integral for the third region, so that's pi, and again now we go from -1 to 0 in the y direction, big radius squared minus little radius squared. So the sum of these three integrals gives you the entire volume of just that middle part, right, the middle area of intersection revolved. So I'm not doing those two end pieces there, right? I mean, it's already complicated enough, so let's just focus on that middle region. And that was just about x equals 3. Now when you do it about x equals -4, the only thing you have to be paying attention to is what your radius is going to be, right? So I'm not going to do that, I'll leave that as an exercise. But I will do, for the last part, I will look at revolving about y equals 4 using cylindrical shells. So that'll be the last of this volume problems that I'm going to do. Just let me get my sheet of paper set up. So this is 34E, and I'm doing part Roman numeral 3. Okay, so I'm doing this about y equals 4 using cylindrical shells. So again, let me quickly sketch my region. And a typical cylindrical shell is a horizontal piece, right? So remember what I was arguing before. If I'm revolving about something that is now horizontal in the cylindrical shell method, I'm going to be doing an integral with respect to y. Okay, so I'm here. So I know it is an integral with respect to y, so of course I'll be using those functions. So So now let's take a look at what the radius rho would be, right? So y equals 4 is up here. The radius rho would be just 4 minus the y coordinate. But what's going to happen is I revolve each of these pieces, region 1, region 3, and region 2 in the middle, is what I'm going to get is different heights. So the height over region 1, notice, is going to be the square root function is more positive, right? When I think of it horizontally, it's more to the right. So it's the square root minus the 4th degree. So I have minus
and I'm subtracting the negative root, which is that part of region 3, right? So minus the negative root of that expression, y plus 5 square root, and then plus 3, all under the square root. For height of region 2, is the positive root minus the negative root, because this is the height that we're considering. So it's going to be really twice the positive root. And the height for region, for the last part, is now positive root for the 4th degree minus the positive root for the polynomial, just like so. So now I can set up the integrals. Right, so the volume is going to be, let's see, it's going to be 2 pi integral y goes from, we saw this was minus 1 to 0 of rho, and that's 4 minus y times h over region 1 dy. That's just taking care of region 1. Now let's add to this the integral for region 2. When I go, y goes from 0 to 4, rho is the same, but the h will be different. And lastly, the last part is going to be 2 pi integral, again goes from minus 1 to 0. 4 minus y is the radius, rho, and what I have is positive root here, so just the h, right, the one that we computed earlier, minus square root of minus y. And notice it's no coincidence that the first and the last integral look the same, and the reason for that is these two regions are symmetrical when I revolve them about a horizontal axis, right? So they should be the same, and I could have just done it with two integrals, multiplying, counting this one twice. And that is 34 Roman numeral 3. Roman numeral 4 is going to be very similar, except the radius rho is going to change. So I'll leave that as an exercise for you guys to do. And for the last problems over here, I'm just going to quickly mention them. For number 35, we did a very similar problem in tutorial, right, in our last tutorial. So you should all be familiar on how to handle that. So I'm not going to cover that again. And problems 36 and 37 were covered in detail in class, in the last class on Wednesday. So again, I will not cover that in the video again. Alright, hope this helps, and good luck on the final exam.